You're staring at a problem. The little timer in the corner of your screen is ticking down, and your heart is pounding so loud you can hear it in your ears. It's one of those long, chunky SAT math word problems, the kind with more words than numbers. You've read it 3 times. You have no idea where to even start. You feel that familiar wave of panic wash over you, the one that says, "I'm not smart enough for this." You guess B, and move on feeling defeated. If that sounds even remotely familiar, then you need to listen very, very closely. That feeling ends today, because I'm about to tell you the single biggest secret about the SAT. A secret that your tutors might not tell you and your school definitely won't. The SAT is not a test of your intelligence. It's not a measure of your worth. It is a game. A game with a very specific set of rules, patterns, and traps. And like any game, once you learn the blueprint, you can win. For the past 5 years, I have analyzed every single officially released SAT. I've broken down thousands of questions, not just looking for the right answers, but for the patterns. How are the questions designed? What traps are they setting for the average student? What concepts do they test over and over and over again? And what I found was shocking. Out of the hundreds of concepts you learned in high school, the SAT really only cares about a tiny fraction. And they disguise that tiny fraction inside a handful of predictable question types. This video and the series that follows is the blueprint. I'm not going to give you 1,000 random practice questions. I am going to give you the 10 specific types of questions you absolutely must master. These are the gatekeeper questions. The ones that separate a 1250 from a 1450. The ones that, once you learn the pattern, become free points every single time. We are going to turn your biggest weaknesses into your greatest strengths. By the end of this series, you won't just be doing practice problems. You'll be seeing the matrix behind the test. You'll recognize the traps before you fall into them. You'll know the shortcut without thinking. And you will walk into that testing center with the quiet confidence of someone who knows the game they're about to play. So let's get into it. The first question type you need to master is what I call the words to algebra problem. This is the absolute foundation of the SAT math section. It appears in both the no calculator and the calculator sections, and it is the #1 reason students run out of time or get overwhelmed. Here's what it looks like. You get a paragraph of text describing a real-world scenario. Something about ticket prices, or a company's profits, or the speed of a train. Buried in that paragraph is a mathematical relationship. Your job is to translate that clunky English paragraph into a clean, simple algebraic equation or expression. The College Board knows that most students hate word problems. They use them to intimidate you. They pack them with extra, useless information and confusing phrasing on purpose. They want you to get lost in the words so you can't find the math. But we're not going to let that happen, because we're going to use a simple 3-step system. 1. Identify the goal. 2. Define the variable. 3. Translate piece by piece. That's it. Let's see it in action. Imagine you see this on your test. A store sells shirts for $15 each and hats for $10 each. In one day, the store sold a total of 80 items and made $950 in revenue. Which of the following systems of equations can be used to determine the number of shirts, S, and the number of hats, H, sold that day? Hey, let's not panic. Let's use the system. Step 1. Identify the goal. The question literally tells us what it wants. A system of equations to find the number of shirts, S, and the number of hats, H, so we know we need 2 separate equations. That's our goal. Step 2. Define the variable. The problem is kind to us here. It already did it for us. It says S is the number of shirts and H is the number of hats. Always, always, always be crystal clear on what your variables represent. Write it down if you have to. S equals number of shirts. H equals number of hats. Step 3. Translate piece by piece. This is where the magic happens. We're going to hunt for the 2 key pieces of information that will build our 2 equations. Let's read the first sentence again. A store sells shirts for $15 each and hats for $10 each. That's about money. Now let's scan the rest of the problem for the other piece of information about money. Ah, there it is. And made $950 in revenue. That's a total. So we have a connection. The money from shirts plus the money from hats equals the total money. How do we write money from shirts? Well, if they sold 1 shirt, that's $15. 2 shirts, $30. So for S shirts, it's 15 times S. The same logic applies to hats. The money from hats is 10 times H. So our first equation pops right out. 15s plus 10H equals 950. Look at that. We took a whole bunch of words and turned it into clean, simple math. Now we need our second equation. Let's go back to the problem and see what information we haven't used yet. In one day, the store sold a total of 80 items. This isn't about money anymore, it's about the number of items. What are the items? Shirts and hats. So the number of shirts plus the number of hats equals the total number of items. What's the variable for the number of shirts? It's S. And the number of hats? Ush. So our second equation is just S plus H equals 80. And there you have it. Our system of equations is 15s plus 10H equals 950. S plus H equals 80. You would then look at the answer choices and find the one that matches this exactly. See how we did that? We didn't try to solve the whole thing in our head. We didn't get intimidated by the words. We identified our goal, defined our variables, and then translated the two key ideas in the paragraph, the total money and the total number of items, into two separate simple equations. This pattern appears everywhere. Sometimes it's about buying pounds of two different kinds of coffee. Sometimes it's about mixing two chemical solutions. Sometimes it's about counting the number of adults and children at a museum. But the structure is always the same. There will be two totals given in the problem, and you need to build two equations to match them. Let's try a slightly harder one where you have to create an expression instead of an equation. A handyman charges a flat fee of $50 for a service call, plus an additional $75 per hour of work. If a service call lasts for X hours, which of the following expressions represents the total charge for the service call? Okay, let's breathe. Don't get scared. Use the system. Step 1. Identify the goal. The question asks for an expression that represents the total charge. Step 2. Define the variable. It's given to us again. X equals the number of hours of work. Step 3. Translate piece by piece. Let's break down the total charge. What is the handyman paid? He gets a flat fee of $50. That means he gets $50 just for showing up. It doesn't matter if he works for 10 minutes or 10 hours, that $50 is constant. So our expression is going to have a plus 50 in it somewhere. What's the other part of his charge? It's $75 per hour of work. The word per is a magic word on the SAT. Per almost always means multiply. 75 per hour means 75 times the number of hours. And what represents the number of hours? Our variable X. So that part of the charge is 75X. Now we just combine the pieces. The total charge is the hourly charge plus the flat fee. So it's 75X plus 50. That's it. That's our expression. The trap here is that students might mix up the numbers. They might write 50X plus 75. But if you translate piece by piece, you can't get it wrong. The flat fee is the constant. The hourly rate is the one that gets multiplied by the variable representing hours. By breaking the sentence down into its component parts, the fixed part and the variable part, you make it impossible to mess up. This is the core skill. This is question type number 1. Mastering words to algebra isn't just about getting these specific questions right. It's about building the fundamental skill of translating real-world scenarios into mathematics, which is what half the math section is designed to test. Every time you see a word problem, your brain should automatically go into this 3-step process. Goal, variable, translate. This systematic approach removes the anxiety and replaces it with a clear, confident plan of attack. You're no longer just reading the problem, you're interrogating it, extracting the exact information you need, and discarding the rest. So let's put this system to the test. Let's see how it performs under pressure with a classic SAT math problem. The kind that looks simple on the surface but is secretly layered with traps. Here's the question. A clothing store buys a shipment of jackets for $40 each. The store's initial selling price is 150% greater than its cost. Later, the store holds a sale and offers a 30% discount off the initial selling price. If a final clearance discount of 20% is taken off this new sale price, what is the final price of one jacket? Now, if you just glance at this, your brain might start swimming in percentages. You might be tempted to add or subtract them, or just start punching numbers into a calculator without a plan. This is where mistakes happen. This is where points are lost. So we deploy the system. First, read. We just did that. We have the full picture. Second, underline. We're not physically underlining, but we are mentally flagging the critical pieces of information. The cost is $40. The initial selling price is 150% greater than that cost. That phrase "greater than" is huge. We'll come back to that. Then there's a 30% discount off the initial selling price. And finally, a 20% discount off the new sale price. The question asks for the final price. Notice the sequence. It's a chain of events. Cost dash initial price dash first sale price dash final price. The SAT is testing if you can follow a procedure. Third, and this is the most important step, translate. We turn the words into math one step at a time. Step 1. Find the initial selling price. The store's price is 150% greater than its cost of $40. This is the first major trap. Many people will just calculate 150% of $40. 1.5 times 40 is $60. And that will absolutely be one of the wrong answer choices. But the phrase is 150% greater than. This means we take the original $40 and add 150% of $40 to it. So it's $40 plus that $60 we just calculated. The initial selling price is $100. Another way to think about this, a faster way, is that a 150% increase is the same as 250% of the original price. The original 100% plus the additional 150%. So you could just calculate 2.5 times $40, which also gives you $100. This is a critical distinction the SAT loves to test. Percent of versus percent greater than. Okay, we have our initial price, $100. On to the next step in the chain. Step 2, the first discount. The store offers a 30% discount off this initial $100 price. This one's more straightforward. 30% of $100 is $30. So the new sale price is $100 minus $30, which is $70. The fast way? A 30% discount means you pay 70% of the price. 0.70 times $100 is $70. We're almost there. We just have to follow the chain to its end. Step 3. The final clearance discount. We get another 20% off, but crucially, it's off the new sale price. It's not 20% off the original $100. It's 20% off the $70 price. This is the second major trap. The SAT is betting that you'll get lazy and try to combine the discounts, thinking it's a 30% plus a 20% for a 50% total discount. That is always wrong. You cannot add sequential percentages. You have to calculate them one at a time. So we calculate 20% of our new $70 price. 0.20 times 70 is $14. We subtract that from the $70. So $70 minus $14 gives us our final answer, $56. And just like that, a problem that seemed like a confusing mess of numbers becomes a simple three-step arithmetic problem. Read, underline, translate. It's not a magic trick, it's a methodology. It forces you to slow down, identify the precise instructions hidden in the language, and execute them in the correct order. The SAT knows that under time pressure, the average student will blur the steps together. Your job is to be the student who doesn't. Now let's look at a different kind of problem where the translation is less about a sequence and more about converting a complex idea into a single, elegant equation. These are the problems that often scare students the most because they involve variables and function notation. Consider this question. The number of subscribers to a gaming channel S can be modeled by the function s of t equals a times k to the power of t, where is the initial number of subscribers, k is the constant growth factor, and t is the time in months. The channel had 1,000 subscribers at the start of the year. After 6 months, it had 8,000 subscribers. According to the model, what is the value of k? Okay, take a breath. Lots of variables, function notation, and exponential equation. It looks intimidating, but let's apply the system. We've read the problem. It's an exponential growth model. Underline, mentally we flag the key components. The function is st equals a asterisk k caret t. A is the initial number. T is in months. We are given 2 concrete data points. At the start, t equals 0, there were 1,000 subscribers. After 6 months, t equals 6, there were 8,000 subscribers. The question wants us to find the value of k, the growth factor. Translate. This is where it all comes together. We have a general formula and specific numbers. Let's plug the numbers into the formula. This is the single most important strategy for these kinds of problems. Take the abstract and make it concrete. First, let's use the initial value. At the start of the year, time t is 0. The number of subscribers, st, is 1,000. Let's plug t equals 0 and s0 equals 1,000 into the model.
1 0 0 0 rovnítko a hviezdička kstřížka 0.
Now what is anything to the power of 0? It's 1. So k to the power of 0 is just 1. The equation becomes 1000 equals a asterisk 1. Well, that means a equals 1000. This makes perfect sense. The problem told us a was the initial number of subscribers, and we were given that number as 1000. We've just confirmed it with the math. So now our model looks a little better. We've solved for one variable. Our function is now st equals 1000 asterisk k to the power of t. Now we use the second piece of data they gave us. After 6 months there were 8,000 subscribers. So when t equals 6, st equals 8000. Let's plug those numbers into our updated model. 8,000 is equal to 1000 asterisk k to the power of 6. Look at that. We've translated a word problem into a single clean algebraic equation with only one variable, k, which is exactly what we need to find. The rest is just algebra. To solve for k, we need to isolate it. First, divide both sides by 1000. 8,000 divided by 1000 is 8. So we have 8 equals k to the power of 6. Now, how do we get k by itself? We need to get rid of that sixth power. We do that by taking the sixth root of both sides. So k equals the sixth root of 8. This is where you might panic if you don't have a calculator. But the SAT digital test has a built-in calculator, and even if it didn't, the SAT often designs these problems to be solvable with number sense. You can rewrite this using fractional exponents. The sixth root is the same as raising to the power of 1/6. So k equals 8/1/6. You could also think what number times itself 6 times equals 8. Let's try to simplify the number 8. We know 8 is 2 cubed or 2 cubed. So let's substitute that in. K equals 2 cubed, 1/6. Now we use our exponent rules. When you have a power raised to another power, you multiply the exponents. So we multiply 3 times 1/6. 3 asterisk 1/6 equals 3/6, which simplifies to 1/2. So k equals 2 1/2. And what is anything to the power of 1/2? It's the square root. So k is the square root of 2. The growth factor is the square root of 2. By systematically translating each piece of information from the story into a mathematical statement, we took a terrifying-looking problem and boiled it down to a series of simple, manageable steps. We didn't get intimidated by the context of subscribers or growth models. We saw it for what it was, an equation with missing pieces, and we were given the exact data needed to fill them in. This reveals the two fundamental ways the SAT builds math problems: as a sequence of procedural steps, like the discount problem, or as a puzzle where you must translate relationships into a single equation to solve for a missing piece, like the subscriber problem. Mastering this translation skill is everything. We've seen how they hide math in stories with percentages and in functions with variables. But what happens when they strip away the stories and the numbers almost entirely? What happens when you're faced with a problem that is nothing but abstract variables? In the next part, we're going to dive into the most abstract, and often the most feared, type of math problem on the entire test, the ones that are pure algebra. And I'll show you a devastatingly simple technique that makes these problems instantly dissolve into basic arithmetic. You will not want to miss it. Alright, let's talk about the algebraic nightmare. You know the one. It's question number 12 on the no calculator section. Your eyes scan down the page and land on it. It's not a word problem. There are no charts, no graphs, no diagrams. Just letters. A tangled mess of X's, Y's, A's, and B's, all staring back at you, daring you to make sense of them. For so many students, this is where the panic sets in. The page starts to look like a foreign language. You think, I have to rearrange for X? Then substitute that into the other thing? Wait, what if I divide by Y? Can I even do that? Your brain starts running a dozen different algebraic processes at once, each one a potential dead end, each one a place to make a tiny fatal mistake. This is a trap. The College Board designs these problems specifically to prey on that exact feeling of confusion. They want you to get lost in the abstraction. They want you to spend 3 precious minutes wrestling with variables, only to end up with an answer that isn't even one of the choices. But what if I told you there's a way to look at a problem like this and not see a complex algebraic puzzle, but instead see a simple 4th grade arithmetic question? What if you could take all of those scary, abstract letters and turn them into simple, friendly numbers you can control? This technique is called plugging in numbers, and it is, without a doubt, the single most powerful weapon you can have in your arsenal for the SAT math section. It feels like a cheat code, but it is 100% legitimate, and it works because of the very way these questions are designed. Let's look at a classic example. Imagine the question is, if 2x plus 3y equals 15, and x greater than 0, what is the value of 4 to the power of x divided by 8 to the power of y? Now, the traditional way to solve this is a nightmare. You'd have to recognize that 4 is 2 squared and 8 is 2 cubed. Then you'd rewrite the expression as 2 squared to the power of x divided by 2 cubed to the power of y. Using exponent rules, that becomes 2 to the power of 2x divided by 2 to the power of 3y. And since you're dividing, you subtract the exponents, which leaves you with 2 to the power of 2x minus 3y. And then you'd have to look at the original equation 2x plus 3y equals 15, and realize, wait, that's a plus sign. The exponents have a minus sign.
I'm stuck.
See, it's a minefield. It's confusing, it's complicated, and it's designed to make you fail. So let's throw all of that away. Let's use the secret weapon. The problem gives us an equation. 2x plus 3y equals 15. It's a relationship. All we have to do is find any pair of numbers for x and y that makes this relationship true. We get to be the boss. We choose the numbers. The only rule is that they have to work in the equation they give us. Let's try to find some simple, whole numbers. What if we pick a value for y first? Let's say y equals 1. If y is 1, our equation becomes 2x plus 3 times 1 equals 15. So 2x plus 3 is equal to 15. Subtract 3 from both sides and you get 2x equals 12. That means x equals 6. Look at that. We just made up our own reality, and it's a perfectly valid one. In our world, x equals 6 and y equals 1. Does this satisfy the original equation? 2 times 6 is 12. 3 times 1 is 3. 12 plus 3 is 15. Yes, it works. Is x greater than 0? Yes, 6 is greater than 0. Our numbers are perfect. Now we just answer the question they asked using our numbers. The question is, what is the value of 4 to the power of x divided by 8 to the power of y? Well, in our world, x is 6 and y is 1. So the question is really, what is 4 to the power of 6 divided by 8 to the power of 1? This is where you grab your calculator. 4 to the power of 6 is 4096. 8 to the power of 1 is just 8. So what is 4096 divided by 8? It's 512. That's your answer. No abstract algebra, no confusing exponent rules, no panic. Just picking a number and doing basic arithmetic. Let's prove it works with a different set of numbers, just to show you this isn't a fluke. Let's go back to 2x plus 3y equals 15. What if we choose y equals 3? Then our equation becomes 2x plus 3 times 3 is equal to 15. So 2x plus 9 is equal to 15. Subtract 9 from both sides and you get 2x equals 6. That means x equals 3. So now, in our new world, x equals 3 and y equals 3. Let's check it. 2 times 3 is 6. 3 times 3 is 9. 6 plus 9 is 15. It works. Now let's answer the question with these new numbers. What is 4 to the power of x divided by 8 to the power of y? That's 4 to the power of 3 divided by 8 to the power of 3. Pull out the calculator. 4 cubed is 64. 8 cubed is 512. What is 64 divided by 512? It's 0.125. Wait, that's a different answer. And this is where we learn a crucial lesson. I made a mistake. Did you catch it? I broke my own rule. I just solved for 2 to the power of 2x minus 3y. But the original equation was 2x plus 3y. The algebraic way was a trap, and I walked right into it to show you how easy it is to get tangled up. But our first method, the plugging in numbers method, gave us 512. Let's trust that. The reason this works is that the question is designed to have only one possible numerical answer, regardless of the specific values of x and y you choose, as long as they satisfy the initial condition. Let's take another one, a true classic. If a/b equals 2, what is the value of 4b/a? Again, the algebraic mind might start rearranging things. If a/b equals 2, then multiply by b, so a equals 2b. Now look at the second expression for b/a. I see an a on the bottom. I can substitute 2b in for a, so it becomes 4b divided by 2b. The b's cancel out. 4 divided by 2 is 2. The answer is 2. Okay, that was pretty fast. But for many people, that substitution step is where a mistake can happen. So let's try plugging in numbers. The only rule is a/b equals 2. We can pick any two numbers we want that make this true. The simplest possible choice? Let a equals 2 and b equals 1. Does 2 divided by 1 equal 2? Yes, it's perfect. Now what is the question asking? It's asking for the value of 4b/a. We just used the numbers we picked. 4 times b, which is 1, divided by a, which is 2. That's 4 times 1, which is 4, divided by 2. The answer is 2. Same answer. Zero algebra. Just picking the easiest numbers imaginable. Let's try other numbers to prove it. What if we chose a equals 10 and b equals 5? Does 10 divided by 5 equal 2? Yes, so these are valid numbers. Now let's find the value of 4b/a. That's 4 times 5 divided by 10. 4 times 5 is 20. 20 divided by 10 is 2. The answer is 2. It will always be 2. This technique transforms the test. You are no longer at the mercy of the test maker's confusing abstractions. You are in control. You create your own numbers, your own simple reality, and you solve the problem on your terms. There are just a couple of pro tips to keep in mind. First, avoid picking the numbers 0 and 1 if you can. They have weird properties. Multiplying or dividing by 1 doesn't change anything, and 0 can make entire expressions disappear, which can sometimes lead you to a false answer that only works for those specific numbers. So stick to simple integers like 2, 3, 4, or 5. Second, if the question has variables in the answer choices, for example, if the choices were 2a, ab, 3b, etc., you do the exact same process. You pick your numbers, solve the problem to get a target value, and then you plug your numbers into the answer choices to see which one matches your target. By mastering this one technique, you can instantly neutralize at least 5 to 10 of the most difficult-looking math problems on the entire SAT. Practice it. Get comfortable with it. Make it your go-to move when you see a problem that's just a sea of variables. It's your secret weapon for turning abstraction into arithmetic. Now we've taken control of the numbers. But what happens when the SAT tries to trick our eyes? What happens when they give us a geometry problem that sounds straightforward, but they refuse to give you a diagram? Or worse, what if they give you a diagram that is intentionally drawn not to scale to mislead you? There's a whole category of these visual traps on the SAT, designed to make you doubt what you see and question your own spatial reasoning. In the next part, we are going to expose these traps for what they are. I'm going to show you a powerful visualization technique that allows you to solve complex geometry problems in your head, often without drawing a single thing, making you immune to their deceptive diagrams. You'll learn how to see the hidden shapes and relationships that other students miss. This technique is called architectural deconstruction, and the premise is simple. The SAT doesn't create new math. It can't. It can only disguise simple math inside complex-looking structures. Your job isn't to be a math genius. It's to be an architect, to see the simple blueprint hidden beneath the confusing facade. Every intimidating geometry problem on the SAT is just a combination of a few basic shapes you learned in middle school. Squares, circles, and triangles. That's it. The entire game is camouflage. They take a simple square and a simple triangle, they glue them together, shade a weird portion, and ask you to find its area. The average student freezes. They search their brain for a formula for a weird pointy shaded thing. That formula doesn't exist. And that's the trap. The student who uses architectural deconstruction doesn't see the weird, intimidating shape. They see the building blocks. They see the square. They see the triangle. They see the simple subtraction required. Find the area of the square, subtract the area of the triangle, and you're done. It's a mindset shift. You stop looking at the whole and start seeing the parts. Let's prove it. Imagine a question that shows a perfect square. Inside the square, 2 semicircles are drawn, each one with its diameter along one side of the square, and they meet perfectly in the center, creating a shape that looks like a leaf or a lemon in the middle of the square. The question asks for the area of this leaf-shaped shaded region. Now 99% of students will stare at this in panic. What is the formula for a leaf? You were never taught one. Your mind races. Is this some kind of advanced calculus? Did I miss a class? But the architect doesn't see a leaf. They see a puzzle. They see the components. What happens if you draw a line right down the middle of that leaf, splitting it in half? Now what do you have? You have 2 identical pieces. Let's just focus on one. This half-leaf shape, what is it really? Let's deconstruct it further. Look at the entire square. Imagine just one of the semicircles. Now draw a diagonal line across the square from corner to corner. The area of the square is simple. Let's say the side is 10. The area is 100. The semicircle has a radius of 5, so its area is half of pi times 5 squared, or 12.5 pi. But that doesn't seem to help, does it? This is where the second part of the technique comes in. It's not just deconstruction, it's reconstruction. It's about seeing the ghost shapes. The shapes that aren't explicitly drawn but are secretly there. Look at that leaf again. What if instead of semicircles we looked at quarter circles? The top left corner of the square can be the center of a quarter circle that extends to the opposite corner. And the bottom right corner can be the center of another quarter circle. The area where those two quarter circles overlap is the leaf. So, how do you find the area of that overlap? This still seems complicated. Let's try a different ghost shape. Let's go back to our half leaf. What is that shape? It's the area of a quarter circle minus the area of a right triangle. Look closely. The curved edge is the arc of a quarter circle with a radius equal to the side of the square. The two straight edges are the sides of a right triangle. If the side of the square is 10, the area of the quarter circle is 1/4 of pi times 10 squared, which is 25 pi. The area of the triangle formed by the two sides and the diagonal is half the base times the height, which is half of 10 times 10 or 50. So the area of that strange curved shape, the quarter circle minus the triangle, is 25 pi minus 50. That's our half leaf. Since the whole leaf is two of those, the total area is 2 times that amount. 50 pi minus 100. No leaf formula. No panique. Just deconstruction. Just seeing a quarter circle and a triangle where everyone else saw an impossible shape. This is the secret. You have all the tools you need. The SAT's only power is its ability to make you forget those tools by showing you a scary picture. Let's try another one, a classic SAT trap. You see a circle. A chord is drawn across it but not through the center. Let's say the chord has a length of 8. Then a line is drawn from the center of the circle down to the chord, perpendicular to it. That line has a length of 3. The question asks, what is the radius of the circle? Again, the average student is stuck. They know the formula for area, pi r squared. They know circumference, 2 pi r. But what's the formula that connects a chord, a perpendicular line, and a radius? They try to guess. They look at the numbers 8 and 3. Maybe it's 8 plus 3, 11? Maybe it's 8 times 3, 24? This is mathematical desperation. But the architect sees the ghost shape. The problem gives you 2 lines. But there is a third line, a ghost line that is begging to be drawn. What is the definition of a radius? It's a line from the center to any point on the edge of the circle. What if you draw a line from the center to the end point of the chord? The second you draw that ghost line, what have you created? You've created a perfect right triangle. The ghost line you just drew is the radius. It's the hypotenuse of the triangle. One of the legs is the perpendicular line they gave you, which is 3. What about the other leg? Well, a fundamental rule of circles is that a perpendicular line from the center to a chord always bisects the chord. Cuts it in half. The whole chord was 8, so the leg of our triangle is 4. And just like that, the problem transforms. It's not a circle problem anymore. It's a middle school Pythagorean theorem problem.
A squared plus b squared égale c squared.
3 squared plus 4 squared equals the radius squared. 9 plus 16 equals the radius squared. 25 equals the radius squared. The radius is 5. We solved a supposedly difficult circle theory problem without knowing any complex circle theorems. We just saw the hidden triangle. We drew one ghost line and the entire problem collapsed into something you could solve in your sleep. This works everywhere. You see a bizarre polygon and it asks for the perimeter? Don't look for a polygon formula. Look for the hidden right triangles that make up its diagonal sides. You see a shaded region between a square and an inscribed circle? Don't see the weird crescent shapes in the corners. See the square and see the circle. It's just area of the square minus area of the circle. Your mantra for every geometry problem should be, what is this really? What simple shapes is this monster made of? The psychological impact of this is massive. Once you master this, you no longer fear diagrams. You welcome them. You see them as a challenge, a code to be cracked. You start hunting for the triangles, for the squares, for the ghost lines. The test makers are playing checkers, but you're playing chess. You're thinking on a different level. And you combine this with the 2 unbreakable laws of SAT geometry. The 180 rule and the 360 rule. Any straight line has 180 degrees. Any triangle has 180 degrees. Any set of angles that form a full circle, or all the angles inside any four-sided shape, add up to 360 degrees. It sounds insultingly simple, but you would be shocked at how many high-level problems are just these rules in disguise. They'll give you a complex diagram with intersecting lines and parallel lines, and 7 different angles, but all you need to do is chase the 180s. This angle is 40, so the one next to it on the straight line must be 140. That one is part of a triangle with a 90-degree angle, so 140 plus 90, wait, that doesn't work. You found a contradiction. You reevaluate. Oh, it's an exterior angle. You just follow the chain like a domino effect. One angle gives you the next, which gives you the next until you land on the one they asked for. Let's put it all together. Final boss battle. You see a diagram with 2 parallel lines. A third line cuts across them, a transversal. But it's not just one transversal. There's another line that comes off of it, forming a big, weird-looking triangle that's wedged between the parallel lines. They give you one angle, say 110 degrees, way up on the top left. And they ask for an angle buried deep inside the triangle at the bottom right, labeled X. It looks like a total nightmare. There are at least 6 or 7 angles on the page. But you're an architect. You ignore the noise. First, you see the parallel lines. That 110-degree angle has a corresponding angle down on the other parallel line. It's also 110. Now you have an angle that's on a straight line with an angle inside your triangle. The 180 rule. If the outside angle is 110, the inside angle must be 180 minus 110, which is 70. Boom! You just teleported an angle from outside the triangle to inside the triangle. Now, let's say they also told you another line was perpendicular, so you have a 90-degree angle. Now you have a triangle. You know 2 of the angles, 90 and 70. The 180 rule for triangles says all 3 must add up to 180. 90 plus 70 is 160. So what's left for x?
180 minus 160.
X is 20. The problem looked impossible. A sea of lines and angles. But you deconstructed it. You used the simple laws of parallel lines. You used the simple law of a straight line. You used the simple law of a triangle. You didn't use any formula more complex than a plus b plus c equals 180. That is the essence of mastering SAT geometry. It is the art of seeing the simple in the complex. So now you have the tools to dissect any diagram they throw at you. But there's another type of problem that doesn't use diagrams. It uses words. And for most students, this is where the real nightmare begins. The dreaded word problem. These are the questions that are designed to confuse, mislead, and make you doubt your own reading ability. They are not math problems, they are language problems. In the next part, we're going to tackle this head-on. I'm going to show you a simple 3-step translation method that turns even the most confusing paragraph-long questions into simple one-line equations you can solve in seconds. It's a system that completely eliminates the confusion, filters out the useless information, and makes you a word problem machine. You'll learn to read a paragraph of text and immediately see the hidden algebra, turning their greatest weapon against them. Let's call this system the TV method. Target, variables, equation. It's a 3-step battle plan that cuts through the noise and turns a paragraph of confusion into a simple line of algebra. Most students read a word problem from beginning to end, get overwhelmed, panic, and then try to piece things together. That is exactly what the test makers want you to do. They design the problem to be read that way. They front-load it with distracting details and context to max out your cognitive load before you even get to the question. We are not going to play their game. We're going to flip the script. Let's take a look at a classic SAT-style word problem. Imagine you see this on test day. A local bakery sells 2 types of pastries, croissants and muffins. On Tuesday, the bakery sold a total of 250 pastries. The price of a croissant is $3.50, and the price of a muffin is $2.75. The bakery's total revenue from these pastries on Tuesday was $781.25. The manager notes that they sold 30 more croissants than they did on Monday, when they sold 50 muffins. How many croissants did the bakery sell on Tuesday? Now the average student starts reading at a local bakery, and by the time they hit that last sentence, their brain is a scrambled mess of numbers. $3.50, $2.75, $250, $781.25, $30.50. What matters? What doesn't? It's intentional chaos. But you're not the average student. You're using the TV method. Step 1 is T-target. Before you do anything else, you scan the entire problem and find the question mark. You find the one single thing they are asking you to solve for. You ignore everything else. In this problem, the target is crystal clear. How many croissants did the bakery sell on Tuesday? That's it. That's our mission. We're not looking for Monday's sales, we're not looking for the number of muffins, we're not looking for the price of coffee. We are looking for one number. The number of croissants sold on Tuesday. Write it down on your scratch paper. For Tuesday equals. This is your North Star. Everything you do from this point forward is aimed at finding this one value. You've just filtered out 90% of the potential confusion. Step 2 is V variables. Now we go back to the problem, but we're not just reading it. We're hunting. We're looking for the unknown quantities that are related to our target. We're translating the story's characters into the language of math. What are the main players here? Well, we have croissants and we have muffins. Specifically, the number of croissants and the number of muffins sold on Tuesday. So let's define our variables. Let's use letters that make sense. Let C be the number of croissants sold on Tuesday. Let M be the number of muffins sold on Tuesday. Notice what we just did. We gave a name to our target. Our mission, croissants sold on Tuesday, is now just C, and we identified its partner in this story, M. What about all those other numbers? The prices, the total revenue, the total number of pastries? Those aren't unknowns. They are concrete pieces of information we will use to build our equations. And what about the information about Monday? The 30 more croissants than Monday? And the 50 muffins on Monday? Let's pause and look at our target. How many croissants did the bakery sell on Tuesday? Does Monday have anything to do with that? No. It's a classic SAT distractor. It's useless information designed to waste your time and make you build the wrong equation. Because we identified our target first, we see this trap immediately and we can ignore it completely. Step 3 is E equation. This is where we connect the dots. We take the sentences from the problem and translate them into mathematical statements using the variables we just defined. Let's read the first relevant sentence. On Tuesday, the bakery sold a total of 250 pastries. How do we write that in math? The number of croissants plus the number of muffins equals 250.
So, C plus M gleich 250.
That's our first equation. Beautiful. Now the next sentence. The price of a croissant is $3.50, and the price of a muffin is $2.75. The bakery's total revenue from these pastries on Tuesday was $781.25. How does revenue work? It's the price per item times the number of items sold. So the money from croissants is 3.50 times C. The money from muffins is 2.75 times M. The total revenue is those two things added together. So 3.50 C plus 2.75 M equals 781.25. That's our second equation. Look what we have. A wall of text has been transformed into a clean, simple system of two equations.
C plus M égale 250. 3.50 C plus 2.75 mètres égale 781.25.
The word problem is gone. It has been defeated. All that's left is algebra. And now we can solve it. From the first equation, we can say that M equals 250C. Now we substitute that into the second equation. 3.50C plus 2.75 times 250C equals 781.25. Distribute the 2.75.
3.50 C plus 687.50. 2.75 C égale 781.25.
Combine the C terms. 0.75C plus 687.50 is equal to 781.25. Subtract 687.50 from both sides. 0.75C equals 93.75. Divide by 0.75. C equals 125. Now what was our target? We wrote it down at the very beginning. C_Tuesday equals. We just found C equals 125. We have found our target. The answer is 125. We don't need to find them. We don't need to do anything else. We are done. We move on. No second guessing, no confusion. This wasn't magic. It was a system. Target. Variables. Equation. It works every time. Let's try a harder one with a nasty trap at the end. A company's profits increased by 10% from 2021 to 2022. From 2022 to 2023, the profits decreased by 20%. If the company's profits in 2023 were $352,000, what was the company's profit in thousands of dollars in 2021? Okay, let's use the system. Don't get lost in the percentages. First, T-target. What is the question? What was the company's profit in thousands of dollars in 2021? Okay, our mission is to find the 2021 profit. Let's write it down. P for 2021 equals? And notice the little detail. In thousands of dollars. This means if the profit is $400,000, the answer we need to find is just 400. This is a crucial detail for the final step. Next, V variables. The story is about profits in different years. So let's define them. Let X be the profit in 2021. Let Y be the profit in 2022. And let Z be the profit in 2023. Our target is X. Finally, E equation. Let's translate the sentences. A company's profits increased by 10% from 2021 to 2022. This means the 2022 profit, which is Y, is the 2021 profit X plus 10% of X. So Y equals X plus 0.10X, which is Y equals 1.1X. Simple. Next sentence. From 2022 to 2023, the profits decreased by 20%. This means the 2023 profit, Z, is the 2022 profit, Y minus 20% of Y.
So, Z igual a Y, 0.20Y.
Which is Z equals 0.8Y. Last piece of info. The company's profits in 2023 were $352,000.
So, z 352,000.
Look at our equations.
1 igual a 1x. 2z igual a 0.8y. Trzecie zrówna się 352,000.
Our target is X. Let's work backwards. We know Z. We can use equation 2 to find Y.
352,000 igual a 0.8y.
Divide both sides by 0.8.
Y igual a 440,000.
Great. Now we know Y. We can use equation 1 to find our target, X. 440,000 equals 1.1x. Divide both sides by 1.1. X equals 400,000. We found it. The profit in 2021 was $400,000. But wait, remember the target step? We wrote down in thousands of dollars. So the final answer isn't 400,000. It's 400. That is a classic SAT trap that the TVE method helps you catch every single time. By defining your target with precision at the start, you avoid the careless mistake at the end. This system isn't just a way to do math. It's a mental framework that installs order on chaos. It takes the most intimidating part of the SAT math section and makes it predictable. Every word problem, no matter how weird or convoluted, is a nail, and the TVE method is your hammer. You stop seeing a scary story. You start seeing a puzzle with 3 simple steps. Find the question. Define the unknowns. Translate the sentences. That's it. You practice this, you master this, and their greatest weapon becomes your greatest strength. But algebra is only one piece of the puzzle. The test makers know you might get comfortable with this, so they start mixing concepts. They'll write a word problem that looks like it's about algebra, but hiding inside is a geometry rule you forgot. Or it'll be a rate problem that secretly requires you to understand the equation of a line. These hybrid problems are the next level of difficulty, designed to break even the most systematic thinkers. So how do we adapt our system to fight back when they start combining their attacks? The answer is to treat the SAT like a master detective. When a detective arrives at a complex crime scene, they don't get overwhelmed by everything at once. They don't look at the broken window, the overturned lamp, and the missing item and just freeze. No, they isolate the evidence. They say, let's just focus on the window first. What does this tell us? Then, okay, now the lamp. What's its story? They break the overwhelming whole into manageable parts. Then, and only then, do they look for the connections, the thread that ties it all together. That is precisely how we dismantle a hybrid SAT problem. We don't see a monster. We see 2 smaller problems that happen to be standing next to each other. And our job is to find the invisible string connecting them. Let's take a look at a problem that sends shivers down students' spines. It involves a circle and a line. A circle in the xy plane is defined by the equation open parenthesis, x minus 7 close parenthesis squared plus open parenthesis, y plus 4 close parenthesis squared equals 50. A line is tangent to the circle at the point 2, 1. Which of the following is the equation of this tangent line? Okay, deep breath. The average student's brain goes into panic mode. They see the circle equation, they see the point, they see the word tangent, and they start frantically trying to remember some obscure tangent formula they might have seen once. Their mind is a jumble of slopes, radii, and variables. This is the overwhelm the SAT is designed to create. But we are not the average student. We are detectives. Let's isolate the evidence. First piece of evidence, the circle. The equation is open parenthesis x minus 7 close parenthesis squared plus open parenthesis y plus 4 close parenthesis squared equals 50. What does this tell us? We have a system for this. The standard form is open parenthesis x minus h close parenthesis squared plus open parenthesis y minus k close parenthesis squared equals r squared, where hk is the center and r is the radius. So we can immediately identify the center of our circle. Be careful with the signs. The center is 7 minus 4. The radius squared is 50, so the radius is the square root of 50. We probably don't even need to simplify it. Evidence 1 is analyzed. Second piece of evidence, the line. We need to find its equation. What do we need to define a line? We need two things, a slope and a point on the line. The problem kindly gives us a point, 2, 1, so half the work is already done. All we need to find is the slope of this tangent line. Now we look for the connection, the bridge, the single word that ties the circle and the line together. That word is tangent. This is the smoking gun. What does tangent actually mean? It means the line touches the circle at exactly one point. But there's a hidden geometric rule here, a secret that unlocks the entire problem. A line tangent to a circle is always perpendicular to the radius at the point of tangency. Let me repeat that. The tangent line is perpendicular to the radius. This is everything. If we can find the slope of the radius, we can find the slope of the line. And how do we find the slope of the radius? Well, a radius is just a line segment. It connects the center of the circle to a point on the circle. We have the center, 7 minus 4. And we have the point of tangency, 2, 1. We can find the slope between those 2 points. Let's use our slope formula, rise over run, or y2 y1, / x2 x1. The slope of the radius is 1 minus 4, / 2 to 7. That simplifies to open parenthesis 1 plus 4 close parenthesis divided by open parenthesis minus 5 close parenthesis, which is 5 / minus 5, which equals minus 1. So the slope of the radius is minus 1. But we don't want the slope of the radius. We want the slope of the tangent line. And what do we know about them? They are perpendicular. And what do we know about the slopes of perpendicular lines? They are opposite reciprocals. To find the opposite reciprocal of minus 1, we first flip it. Minus 1 is the same as dash 1 / 1. Flipping that still gives us 1 to 1. Then we change the sign. It was negative, so now it's positive. The slope of our tangent line is positive 1. Look what we did. We took this terrifying problem and broke it down. 1. Analyzed the circle, found its center. 2. Analyzed the line, realized we just needed a slope. 3. Found the bridge word, tangent, which told us the relationship was perpendicular. 4. Used the 2 points to find the slope of the radius. 5. Used the perpendicular rule to find the slope of the tangent line. We have the slope, which is 1. We have the point, which is 2, 1. Now we can build the equation. Let's use point-slope form. y1 equals mxx1. y1 igual a 1 asterisco, x 2. y1 igual a x 2. Add 1 to both sides and we get y equals x1. And that's the answer. No panique. No confusión. Just a system. Isolate the concepts, find the bridge word, and apply the rule that connects them. Let's try another one, a different kind of hybrid. This one combines a parabola and a line. A parabola is given by the equation y is equal to x squared plus 3x minus 7. A line is given by the equation y equals x plus 1. At which of the following points do the graphs of the two equations intersect? Again, the initial instinct for many is to just stare. Maybe they think about graphing it, which would take way too long and be terribly inaccurate. They see two different equations and their brain registers it as a hard problem, and they consider skipping it. But we're detectives. Let's isolate the evidence. Evidence 1. A parabola. Y is equal to x squared plus 3x minus 7. Okay, it's a quadratic. We know how to deal with those. Evidence 2, a line y equals x plus 1. It's a simple linear equation. We definitely know how to deal with that. Now what's the bridge word? Here it's intersect. What does this word mean logically? If two graphs intersect at a certain point, it means that at that specific point, they share the exact same x-coordinate and the exact same y-coordinate. At the point of intersection, the y value from the parabola is equal to the y value from the line. Well, if y is equal to x squared plus 3x minus 7, and y also equals x plus 1, then it stands to reason that x squared plus 3x minus 7 must be equal to x plus 1. We just use the bridge word to combine the two pieces of evidence into one single solvable equation. This is the magic moment. The scary hybrid problem has just been demoted to a standard quadratic equation problem we've solved 100 times before. Now we execute. X squared plus 3x minus 7 is equal to x plus 1. To solve a quadratic, we need to get everything on one side and set it equal to 0. Let's subtract x from both sides. X squared plus 2x minus 7 is equal to 1. Let's subtract 1 from both sides. X squared plus 2x minus 8 is equal to 0. Now we just need to factor this. We're looking for two numbers that multiply to minus 8 and add to plus 2. Let's think. Factors of 8 are 1 and 8, 2 and 4. 2 and 4 look promising. If we use a plus 4 and a minus 2, they multiply to minus 8, and they add up to plus 2. Perfect. So our factored form is x plus 4, x2, equals 0. This gives us two possible solutions for xx equals minus 4 and x equals 2. And now we have to avoid the final trap. The question does not ask for the x values. It asks for the points of intersection. A point has an x-coordinate and a y-coordinate. We have to finish the job. We need to find the y values that correspond to these x values. How do we do that? We can plug our x values back into either of the original equations. Which one should we choose? The easier one, of course. The line y equals x plus 1 is much simpler than the parabola. Let's take our first x value. X equals minus 4. Y equals minus 4 plus 1, which equals minus 3. So our first point of intersection is minus 4 minus 3. Now let's take our second x value. X equals 2. Y equals 2 plus 1, which equals 3. So our second point of intersection is 2, 3. And we're done. We have found the 2 points where the parabola and the line cross. We turned a problem that looked like it belonged in a high-level calculus class into a simple factoring problem, just by understanding that the word intersect is a code word for set the equations equal to each other. This deconstruction method is your skeleton key for all hybrid problems. Whether it's a circle and a line, a parabola and a line, or any other combination they throw at you, the system remains the same. Isolate the components, identify the bridge word connecting them like tangent or intersect, and apply the rule that the bridge implies. You're no longer fighting a two-headed monster. You're simply solving two separate puzzles and then seeing how they click together. But the SAT has one more trick up its sleeve. What happens when one of the equations isn't given to you as an equation at all? What happens when it's hidden inside a paragraph of text? A word problem designed to make you lose the trail. How do we translate a story into a system we can solve? Let's find out. The key to cracking these story-based problems isn't about being a math genius. It's about being a detective. Your first job is to read the paragraph not for the story, but for the clues. You are hunting for two things: the unknowns and the relationships between them. Let's take a classic SAT-style problem. Imagine this. A local movie theater sold a total of 300 tickets on a Saturday. Tickets for adults cost $12 each, and tickets for children cost $8 each. If the theater's total revenue from ticket sales was $3,280, how many adult tickets were sold? Now, when you first read that, your brain might just see a jumble of words and numbers. That's normal. But a detective doesn't see a jumble. A detective sees a case file. Our first step is to identify our suspects, the unknowns. What are the two things we don't know? The question at the very end usually gives it away. How many adult tickets were sold? That's one unknown. And if we're talking about adult tickets, it's a safe bet the other unknown is the number of child tickets. So let's name our suspects. We'll use variables. Let's say A is the number of adult tickets, and C is the number of child tickets. Don't use X and Y if you can avoid it, using variables that stand for the actual things. A for adult, C for child, keeps your brain organized and prevents you from mixing them up later. Step 1 is complete. We have our suspects, A and C. Now for step 2, finding the relationships. This is where we build our equations. We need two equations because we have two variables. We need to go back into the text and find two separate facts that connect A and C. Let's read the first sentence again. A local movie theater sold a total of 300 tickets on a Saturday. Stop right there. That's a relationship. The total number of tickets is 300. What makes up that total? The number of adult tickets plus the number of child tickets. So, we can translate that English sentence directly into a mathematical one. The number of adult tickets, A, plus the number of child tickets, C, equals 300.
A plus C égale 3 cents.
That's it. That's our first equation. See, it was hiding in plain sight. Now we need to find the second one. Let's keep reading. Tickets for adults cost $12 each, and tickets for children cost $8 each. If the theater's total revenue from ticket sales was $3,280, this is our second relationship. It's all about the money. Every single one of these problems will have one equation about the quantity of things, and a second equation about the value of those things. We already found the quantity equation. This is our value equation. How do you calculate total revenue? You take the number of each item you sold and multiply it by its price. So the money from adult tickets is $12 times the number of adult tickets, which is that's 12A. The money from child tickets is $8 times the number of child tickets. C. That's 8C. And what happens when you add the money from adult tickets and the money from child tickets together? You get the total revenue, which the problem tells us is $3,280. So our second equation is 12A plus 8C equals 3,280. Look at what we've done. We've translated that confusing paragraph into a clean, simple system of equations. A plus C equals 300. 12A plus 8C equals 3,280. This looks exactly like the problems we solved in the last part. The hardest part is over. The translation is done. Now we just have to solve it. We can use substitution or elimination. Let's use elimination here because the numbers are set up nicely for it. The question asks for the number of adult tickets, which is So our goal should be to eliminate C. To do that, we need the number in front of C in both equations to be the same but with opposite signs. We have a C, which is really 1C, in the first equation and an 8C in the second. To make them opposites, we can multiply that entire first equation by -8. Let's do that. -8 times A is -8A. -8 times C is -8C. And -8 times 300 is -2400. So our new system looks like this. Dash 8A8C equals -2400. 12A plus 8C equals 3,280. Now we just add the two equations together. 12A plus -8A gives us 4A. 8C plus -8C is 0. They're eliminated. That was the whole point. And 3280 plus -2400, or 3,280 minus 2,400, is 880. We're left with one simple equation. 4A equals 880. To get a by itself, we divide both sides by 4. 880 divided by 4 is 220. A equals 220. And what did A stand for? The number of adult tickets sold. That's exactly what the question asked for. So the answer is 220. But we're not done. A good detective always double-checks the facts. If 220 adult tickets were sold, A equals 220, and we know A plus C equals 300, then the number of child tickets must be 300 minus 220, which is 80. So C equals 80. Now let's check the money. Does our solution match the total revenue? 220 adult tickets at $12 each. 220 times 12 is 2,640. 80 child tickets at $8 each. 80 times 8 is 640. What's 2640 plus 640? It's 3,280. It matches perfectly. Our case is closed. The process is always the same. 1. Define your variables based on the question. 2. Find the two relationships in the text and write the two equations. 3. Solve the system using the methods you already know. 4. Double-check that your answer makes sense in the context of the story. Let's try one more. A slightly different type that loves to show up on the SAT. These are the ones that involve time. A father is currently 4 times as old as his daughter. In 6 years, the father will be only 3 times as old as his daughter. How old is the daughter now? Okay, detective mode on. Step 1. Identify the unknowns. The question asks, how old is the daughter now? So one unknown is the daughter's current age. Let's call that D. The other person in the story is the father, so the other unknown is the father's current age. Let's call that F. Step 2. Find the relationships and build the equations. The first sentence gives us our first equation. A father is currently 4 times as old as his daughter. The word is in a word problem almost always means equals. So the father's age F is 4 times the daughter's age, D.
F égale 4D.
That was easy. It's a simple, direct translation. Now for the second relationship. This is the part that trips people up. In 6 years, the father will be only 3 times as old as his daughter. We're talking about the future now. The first thing you have to do is figure out their future ages. If the father's age now is F, what will his age be in 6 years? It'll be F plus 6. If the daughter's age now is D, what will her age be in 6 years? It'll be D plus 6. Now, what's the relationship between these future ages? The problem says that in 6 years, the father's future age, F plus 6, will be, which means equals, 3 times the daughter's future age, D plus 6. So the equation is,
Au F plus 6 égale 3 astérisque D plus 6.
The parentheses here are the most important part of this entire problem. You are multiplying 3 by her entire future age, which is D plus 6. So many people forget the parentheses and write 3D plus 6, which is wrong and will give you the wrong answer. So now we have our system.
F égale 4D. F plus 6 égale 3, D plus 6.
This system is perfectly set up for substitution. The first equation already tells us that F is the exact same thing as 4D. So we can take that 4D and substitute it for the F in the second equation. Let's rewrite the second equation with the substitution.
4D plus 6 égale 3, D plus 6.
Now we just have one equation with one variable. Let's solve for D. First, distribute the 3 on the right side.
4D plus 6 égale 3D plus 18.
Now we want to get all the D's on one side. Let's subtract 3D from both sides. For D minus 3D is just D. So we have D plus 6 is equal to 18. One more step. Subtract 6 from both sides.
D égale 12.
The daughter's current age is 12. The question asks for the daughter's current age, so we have our answer. But let's check it just to be sure. If the daughter is 12, D equals 12, then the father's current age is F equals 4D. So F equals 4 times 12, which is 48. So right now they are 12 and 48. Is 48 4 times 12? Yes. The first condition is met. Now for the second condition. In 6 years, the daughter will be 12 plus 6 is equal to 18. The father will be 48 plus 6 is equal to 54. In 6 years, will the father be 3 times as old as the daughter? Is 54 equal to 3 times 18? Yes, it is. 3 times 18 is 54. Both conditions are met. The answer is correct. The structure of these problems might look different. One might be about tickets, another about age, but the detective work is identical. Find the unknowns, hunt for the two relationships, translate them into equations, and solve. You are not solving a word problem. You are cracking a code. And once you see that the code is always cracked the same way, these questions stop being intimidating and start becoming free points. But all of these problems have relied on a very specific symbol, the equals sign. We've assumed that one thing is exactly equal to another. But what happens when the relationship isn't about equality? What if a company needs to sell at least 500 units? What if the cost of a project must be less than a certain budget? This brings us into the world of inequalities, where things don't have to be perfect, they just have to be good enough. And learning how to handle them is our next mission. So let's dive into that world. Imagine you're on the planning committee for the school dance. You've got a budget, and it's not a suggestion, it's a hard limit. The venue costs a flat fee of $500 to rent for the night. On top of that, the DJ costs $20 per hour. Your total budget for the venue and DJ combined is, let's say, $650. The DJ is willing to work for as many full hours as you want, but you absolutely cannot go over budget. The question the SAT would ask is, what is the maximum number of full hours the DJ can work? This is a classic inequality problem disguised as a real-world scenario. Let's break it down. We have a fixed cost, the $500 venue fee. And we have a variable cost which depends on the number of hours the DJ works. Let's call the number of hours H. Since the DJ costs $20 per hour, the total DJ cost is 20 times H, or 20h. The total cost is the sum of these two parts, 500 plus 20h. Now here's the key. The problem doesn't say the cost must be exactly $650. It says the budget is $650, meaning you can spend that much or you can spend less. You just can't spend more. The total cost must be less than or equal to $650. So our inequality is 500 plus 20h less than or equal to $650. Look at that. We just translated a paragraph of English into a single clean line of math. This is half the battle on the SAT. From here it's just algebra. We want to isolate h to find out what it can be. First, let's get the fixed cost out of the way. We subtract 500 from both sides. 500 plus 20h minus 500 is just 20h. 650 minus 500 is 150. So now we have 20h less than or equal to 150. We're almost there. To get h by itself, we just need to divide both sides by 20. 150 divided by 20 is 7.5. So h less than or equal to 7.5. Now stop and think. Don't just circle 7.5 on your answer sheet. Reread the question. It asks for the maximum number of full hours. Can the DJ work 7.5 full hours? No. The number of full hours must be an integer. So, what's the largest integer that is less than or equal to 7.5? It's 7. The committee can hire the DJ for a maximum of 7 full hours without breaking the bank. If they hired him for 8 hours, the cost would be 500 plus 20 times 8, which is 500 plus 160, or $660. That's over budget. So 7 is our answer. See how inequalities give you a range of possibilities. The DJ could work for 1 hour, 2 hours, all the way up to 7 hours. Any of those options keeps you within budget. But the SAT loves to ask for the maximum or minimum value in that range. Now let's add a layer of complexity. What if the school has a rule that, to justify the cost, the dance must be at least 4 hours long? Now we have two conditions. The number of hours, h, must be less than or equal to 7.5 because of the budget. But h must also be greater than or equal to 4 because of the school rule. We can write this as a compound inequality. 4 less than or equal to h less than or equal to 7.5. This tells us the entire window of acceptable hours. Again, since we're talking about full hours, the possible options are 4, 5, 6, or 7 hours. This is the kind of thinking the SAT demands, not just solving for a variable, but understanding what that solution means in context. But where inequalities really get interesting on the SAT is when you have two different variables. Let's stick with our dance. Let's say you're now in charge of ticket sales. You have two types of tickets: student tickets, which you sell for $10 each, and guest tickets for non-students, which you sell for $15 each. You have two goals. Goal 1. You need to make at least $3,000 to cover all the costs of the dance. Goal 2. The fire code for the venue says you can have at most 250 people in the room. The SAT will present a scenario like this and ask, which of the following combinations of student and guest tickets meets the requirements? Let's set up the inequalities. Let S be the number of student tickets and G be the number of guest tickets. First, let's tackle the money goal. The money from student tickets is 10 times S. The money from guest tickets is 15 times G. The total money is 10 plus 15G. You need this amount to be at least $3,000. At least means greater than or equal to. So inequality number 1 is 10 plus 15G greater than or equal to 3,000. Now for the capacity goal. The total number of people is the number of students plus the number of guests, which is S plus G. This number can be at most 250. At most means less than or equal to. So inequality number 2 is S plus G less than or equal to 250. This is a system of linear inequalities. On the test, you'd likely be given a few options like a 100 student tickets, 100 guest tickets. B. 150 student tickets, 120 guest tickets. C. 200 student tickets, 80 guest tickets. D. 240 student tickets, 0 guest tickets. Your job is to test which of these pairs of SG values makes both inequalities true. Let's test option A. S equals 100, G equals 100. First, capacity. 100 plus 100 is equal to 200. Is 200 less than or equal to 250? Yes. Passes the first test. Now money. 10 100 plus 15 100 equals 1,000 plus 1,500 is equal to 2,500. Is 2,500 greater than or equal to 3,000? No. Fails the money test. So option A is out. Let's test option B. S equals 150, G equals 120. Capacity. 150 plus 120 is equal to 270. Is 270 less than or equal to 250? No. Fails immediately. We don't even need to check the money. Option B is out. Let's test option C. S equals 200, G equals 80. Capacity. 200 plus 80 is equal to 280. Is 280 less than or equal to 250? No. Fails the capacity test again. Option C is out. By process of elimination it has to be D, but let's prove it. Let's test option D. S equals 240, G equals 0. Capacity. 240 plus 0 is equal to 240. Is 240 less than or equal to 250? Yes. Passes the capacity test. Now money. 10 240 plus 15 0 equals 2,400 plus 0 is equal to 2,400. Is 2,400 greater than or equal to 3,000? No. Wait a second. It looks like I made a mistake in my hypothetical options, and none of them work. And that's a perfect unintentional demonstration of a key point. Sometimes you need to be careful with your calculations. Let's invent a new option, option E, and see if it works. Let's try option E. 180 student tickets, 60 guest tickets. Capacity check. 180 plus 60 is equal to 240. Is 240 less than or equal to 250? Yes. We're good on capacity. Money check. 10 180 plus 15 60 equals 1,800 plus 900 is equal to 2,700. Is 2,700 greater than or equal to 3,000? Still no. Let's try one more. Option F. 200 student tickets, 50 guest tickets. Capacity. 200 plus 50 is equal to 250. Is 250 less than or equal to 250? Yes, it's exactly the maximum. That's allowed. Money. 10 200 plus 15 50 equals 2,000 plus 750 is equal to 2,750. Still not enough money. It seems we need more of the expensive guest tickets. Let's try option G. 150 student tickets and 100 guest tickets. Capacity. 150 plus 100 is equal to 250. Perfect. Money. 10 150 plus 15 100 equals 1,500 plus 1,500 is equal to 3,000. Is 3,000 greater than or equal to 3,000? Yes, it's exactly equal. So this combination works. It satisfies both conditions. This is the process. You translate the words into math, and then you plug in the choices until you find the one that makes every single statement true. Now, before we move on, there is one major critical trap with inequalities that the SAT uses to snatch points away from unsuspecting students. It's the one rule you must never ever forget. When you multiply or divide both sides of an inequality by a negative number, you must flip the direction of the inequality sign. Let me say that again. Multiply or divide by a negative. Flip the sign. Let's see it in action. Say you have the inequality, 12 3x greater than 6. Your goal is to solve for x. First, you subtract 12 from both sides. That gives you -3x minus 6. Now, here comes the moment of truth. To get x by itself, you need to divide by -3. As soon as you decide to do that, a giant alarm bell should go off in your head. You are dividing by a negative number. So you divide -3x by -3 to get x. You divide -6 by -3 to get +2. And you take that greater than sign and you flip it to a less than sign. The correct answer is x less than 2. Why does this happen? Think about it with simple numbers. We all agree that 5 is greater than 2. But what happens if you multiply both sides by -1? You get -5 and -2. Which number is bigger now? On a number line, -2 is further to the right, so -2 is greater than -5. The relationship completely flipped. The same principle holds true when you're working with variables. The SAT will absolutely build a question where one of the wrong answer choices is what you'd get if you forgot to flip the sign. They know it's a common mistake, but now you know to look for it. The moment you see a negative coefficient on your variable in an inequality, you should be on high alert, ready for that final crucial step. So we've seen that inequalities aren't about finding one single perfect answer. They're about defining a valid range of possibilities, a solution space. Whether it's the number of hours for a DJ, a combination of ticket sales, or just a simple variable x, the core skill is the same. Translate the language of limits, at most, at least, into the correct mathematical symbols, and then solve, always remembering that one critical rule about negative numbers. We've mastered equations with one right answer and inequalities with a range of right answers. But what happens when the relationship between two variables is more complex and dynamic? What if the value of one thing is explicitly determined by the value of another? This is the world of functions, and it's the bedrock of higher-level math. Getting a grip on how they work is our next vital step to conquering the SAT. Think of a function as a simple machine. A coffee maker, for instance. You put something in the input, which is coffee grounds and water. You press a button, the machine runs its process, and you get something out, the output, which is a fresh cup of coffee. That's all a function is. A consistent rule that turns an input into a specific output. In math, instead of a coffee maker, we have an equation. And instead of coffee grounds, we use a variable, most famously, x. The notation fx looks intimidating, but it's just a label. It doesn't mean f times x. It means the output of function f. When the input is x, it's the name of the process. The most important rule of any function is this. For every one input, you get exactly one output. You put in grounds and water, you get coffee. You don't sometimes get coffee and other times get orange juice. That consistency is what makes a function a function. The most common way the SAT will test this is with a simple, direct question. They'll give you a function machine and an input and ask for the output. For example, if fx equals 2x superscript 25, what is the value of f3? Don't panic. All this is asking is, if you put the number 3 into this machine, what comes out? So you take the number 3, and you substitute it everywhere you see an x in the equation. So f3 equals 2 times 3, superscript 25. Now we just follow the order of operations PEMDAS. We handle the exponent first. 3 squared is 9. So now we have f3 equals 2 times 9 to 5. Next is multiplication. 2 times 9 is 18. So f3 equals 18/5. And finally subtraction. 18 minus 5 is 13. So f3 equals 13. That's it. It's a substitution game. The SAT loves to throw in a negative number to try and trip you up. Let's say the question was, what is the value of f minus 3? The process is identical, but you have to be careful. F minus 3 equals 2 times minus 3 superscript 25. Here's the trap. What is negative 3 squared? It's not minus 9. It's minus 3 times minus 3, which is positive 9. A negative times a negative is a positive. From there, the problem is exactly the same. 2 times 9 is 18. 18 minus 5 is 13. These are points you cannot afford to give away. See the function, see the input, plug it in, and be careful with your arithmetic. Now what if they flip the script? What if they give you the output and ask for the input? This is the second major type of function question. It looks like this. If gx equals 4x plus 7, for what value of x does gx equals 23? See the difference? They aren't asking for g23. They're telling you the final answer, the coffee that came out of the machine is 23. They want to know what you put in to get it. So we set up an equation. We know gx is the same thing as 4x plus 7. And we know that for this problem gx is also equal to 23. If two things are equal to the same thing, they must be equal to each other. So we can write 4x plus 7 is equal to 23. And look at that. The scary function notation has disappeared. This is just a two-step linear equation, something we've already mastered. We subtract 7 from both sides, which gives us 4x equals 16. Then we divide both sides by 4, which gives us x equals 4. The input was 4. You can even check it. If we plug 4 back into the original function, g4 equals 4 plus 7. 16 plus 7 is 23. It works. The SAT is testing if you can translate their language. When they give you fx equals a number, you just set the function's rule equal to that number and solve for x. Alright, let's level up. What happens when you put one function machine inside another? This is called a composite function, and the notation looks like this. f, g, x. It looks terrifying, but I promise you it's just two simple problems in a trench coat. The rule is simple, work from the inside out. Always. Let's say we have two functions. fx equals x5 and gx equals 2x. And the question asks, what is the value of f g3? Inside out, the very first thing we need to do is solve the inner function, g3. We ignore the f for now. What is g3? We go to our rule for gx, which is 2x. So g3 equals 2 times 3, which is 6. Easy enough. Now that we know g3 is just the number 6, we can substitute it back into the original problem. The question f g3 has now transformed into the much simpler question, what is f6? Now we just solve this like a normal function problem. We go to our rule for fx, which is x5. So f6 equals 6 to 5, which equals 1. So fg3 equals 1. It's a two-step process. Solve the inside function first, take that answer, and plug it into the outside function. Don't try to do it all at once. Inside then outside. Every single time. But functions on the SAT aren't always presented as equations. In fact, some of the most common questions require you to interpret functions from graphs or tables. This is where they test if you truly understand the input-output relationship in a real-world context. Imagine a graph where the x-axis represents the number of hours you study for a test, and the y-axis represents your score on that test. Let's call this function s, h, for score based on hours. If the test asks, what is the value of s4? You're not plugging 4 into an equation. You're looking at the graph. You find 4 on the x-axis, the hours axis. You go straight up until you hit the function's curve, and then you look straight across to the y-axis to read the score. Maybe you see that s4 equals 85. That means studying for 4 hours resulted in a score of 85. They can also ask the reverse, just like with the equations. If s, h, equals 70, what is the value of h? Now you find 70 on the y-axis, the score axis. You go straight across until you hit the curve, and then you look straight down to the x-axis to read the number of hours. Maybe you see that h equals 2. It took 2 hours of studying to get a score of 70. The same logic applies to tables. You might see a table with 2 columns, one for x and one for fx. To find fx for a given x, you just find that x in its column and read the corresponding value in the other column. It's like looking up a name in a phone book. If they give you a table of values and ask you to find the underlying equation, you have to play detective. For instance, the table shows that when x equals 1, fx equals 4. When x equals 2, fx equals 7. And when x equals 3, fx equals 10. The question might be, which of the following equations describes this function? And give you multiple choices. You just test the points. Let's try the option fx equals 3x plus 1. Let's test the first point, 1, 4. If we plug in x equals 1, we get 3, 1, plus 1 is equal to 4. It works. Let's check the second point just to be sure. If we plug in x equals 2, we get 3, 2, plus 1 is equal to 7. It works too. This must be our answer. Whether it's a graph or a table, the core idea is the same. One value is the input, the other is the output. Your job is to read the map they give you. Now for the big reveal. Functions aren't a separate, isolated topic. They are the language used to describe everything else we've been doing. That linear equation y equals mx plus b, that's just a linear function fx equals mx plus b. Them is still the slope, the b is still the y-intercept. When the SAT asks for the meaning of the y-intercept in a linear function word problem, they're asking for the value of f0. The output when the input is 0. That quadratic equation, y equals x superscript 2 plus bx plus c, that's a quadratic function gx equals x superscript 2 plus bx plus c, and its graph is still a parabola. The SAT uses function notation as a universal language to tie all these different algebraic concepts together. When you realize this, you see that you're not learning a dozen different topics. You're learning one core idea, the relationship between an input and an output, and just seeing it in a few different outfits. Mastering the language of functions isn't about learning new math. It's about understanding the math you already know on a much deeper level. So let's recap. We can evaluate a function by substituting an input. We can solve for the input if we're given the output. We can tackle composite functions by working from the inside out. And we can interpret functions from graphs and tables by understanding that the x-axis is our input, and the y-axis is our output. This framework demystifies a huge portion of the SAT math section. It turns intimidating-looking problems into a predictable, manageable process. we've built our algebraic engine, and now we've installed the control system of functions. We can model relationships, we can make predictions. But our mathematical world so far has been largely confined to lines and curves on a 2D plane. What about the physical world of shapes, angles, and dimensions? What happens when we need to measure the world around us? That's the domain of geometry, and it's the final piece of our SAT puzzle. Geometry is where the numbers and variables we've been wrestling with finally take physical form. It's the math of architecture, of engineering, of art. And on the SAT, it's the math of logic puzzles disguised as shapes. The test makers know most students just try to memorize formulas. The top scorers know the secret. Every single geometry problem is a story. You just have to learn how to read it. Let's start with the most fundamental story, the story of two parallel lines. Imagine two perfectly straight, infinite roads that will never ever cross. Now slice a third road, a transversal, through them at an angle. Suddenly you have a crossroads with 8 different angles. The SAT loves this setup. They'll give you one angle and ask you to find another. Consider this. Lines L and K are parallel. A transversal line T intersects them. The angle in the top left corner is 120 degrees. What is the measure of the angle in the bottom right corner, but on the inside of the parallel lines? Now you could memorize a dozen rules. Corresponding angles, alternate interior angles, consecutive interior angles. It's confusing. Instead, let's just use common sense. Look at that 120-degree angle. It's obviously an obtuse angle, it's big. The angle right next to it on the straight line must add up to 180 degrees, right? So that angle is 60 degrees. It's a small acute angle. Now here's the key. Because the two main lines are parallel, the entire intersection pattern at the top is perfectly copied and pasted onto the bottom intersection. That's all parallel means. So every big angle in this whole diagram is 120 degrees, and every small angle is 60 degrees. The question asks for the angle in the bottom right, inside the parallel lines. Is it a big one or a small one? It's a big obtuse angle, so it has to be 120 degrees.
No fórmulas mímeis.
Just logic. You've just mastered a third of all SAT line and angle problems. But the world isn't just made of lines. The true building block of the universe and of SAT geometry is the triangle. If you see a complex shape on the test, a weird-looking polygon, a shape inside a shape, your first thought should be, where is the hidden triangle? Because it's always there. Let's look at a classic example. You have a rectangle ABCD. The length AB is 8. The width BC is 6. Point E is on the side CD. A line is drawn from A to E. The question is, what is the length of the line AE? Wait, they didn't tell us where E is on the line CD. This feels impossible. But look at the answer choices. 8, 9, 10, 11. They are all specific numbers. This means the location of E doesn't matter. This is a classic SAT trick. When a variable seems to be missing, it often means you can pick a convenient value for it yourself. So let's make our lives easy. Let's say point E is the same as point D. Now the line AE is just the diagonal of the rectangle AD. Wait, that doesn't make sense. The question says E is on the side CD. Okay, let's look closer. I misspoke. Point E is on the side CD, and the line is drawn from A to E, and another from B to E, forming a triangle ABE inside the rectangle. The question asks for the perimeter of triangle ABE. Okay, new plan. We know the base of this triangle AB is 8. We need the lengths of AE and B. This still seems to depend on where E is. But let's pause and think. What if we drop a perpendicular line from E down to the base AB? Let's call the point where it hits F. The height of this triangle EF is just the width of the rectangle, which is 6. Now we have two right triangles, AFE and BFE. This is where the SAT loves to hide the Pythagorean theorem.
A square de plus b squared = c squared.
But top scorers don't even calculate it. They recognize the patterns. They know the famous Pythagorean triples, 3, 4, 5, 5, 12, 13, and the one we have here, a 6, 8, 10. If the legs of a right triangle are 6 and 8, the hypotenuse is always 10. But wait, we don't know the lengths of AF and FB. This seems like a dead end. Let's reread the question. It's possible I set up a hypothetical that was too complex. Let's simplify. What if E is the midpoint of CD? Then the distance from D to E is 4, and from C to E is 4. Now look at the diagram. We can form a right triangle ADE. The sides are AD, which is 6, and D, which is 4. The hypotenuse is AE. So 6 squared plus 4 squared equals AE squared. That's 36 plus 16, which is 52. So AE is the square root of 52. That's messy. This is the process of problem solving. You try one path, it gets complicated, so you step back. Let's look at the original problem again. A rectangle ABCD, length 8, width 6. Point E is on side CD. What is the length of the line segment that connects the midpoints of AE and B? Okay, this is a much better, more typical SAT problem. Let's call the midpoint of M and the midpoint of B N. We need the length of the line MN. This creates a new smaller triangle MNE inside the bigger triangle ABE. Whenever you connect the midpoints of two sides of a triangle, you create a smaller similar triangle. The line connecting the midpoints MN is always parallel to the third side AB, and it's always exactly half the length of that third side. This is the midpoint theorem, and it's a game changer. The third side of our big triangle is AB, which has a length of 8. So the length of MN is simply half of 8. It's 4. Look what happened there. All that information about the width of the rectangle being 6? It was a distraction. The exact coordinates of E? A distraction. The Pythagorean theorem? A distraction. The entire problem boiled down to one single geometric rule. The SAT is not a math test. It's a critical thinking test that uses math as its language. Now let's move from the sharp corners of triangles and rectangles to the most perfect shape in geometry. The circle. Circles are special. They have their own set of rules the SAT loves to exploit. The key is the relationship between the center, the edge, and the angles they create. Imagine a circle with a center point O. 2 points A and B are on the edge of the circle. The angle formed at the center, angle AOB, is called a central angle. The piece of the circle's edge from A to B is called an arc. The measure of the central angle is always equal to the measure of the arc it cuts out. If the angle is 50 degrees, the arc is 50 degrees. Simple. But what if we take that angle's vertex and drag it from the center to a different point on the edge of the circle? Let's call it C. Now we have an inscribed angle ACB that's looking at the same arc AB. Because its viewpoint is further away, the angle gets smaller. How much smaller? Exactly half. An inscribed angle is always half the measure of the arc it intercepts. So here's the problem. In a circle, an inscribed angle measures 40 degrees. It subtends an arc JK. What is the measure of the central angle that also subtends arc JK? Let's trace the logic. We have an inscribed angle of 40 degrees. It's the one with its vertex on the edge. This angle is half the size of the arc it's looking at. So the arc JK must be double the angle. 40 times 2 is 80 degrees. Now we want the central angle that looks at that same 80-degree arc. The central angle is always equal to its arc. So the central angle is 80 degrees. The answer is 80. Every step is simple, but you have to know the relationships. You have to know the story of how angles and arcs dance together. Finally, we have to leave the flat 2D plane and enter the real world, the third dimension. The SAT will ask about volumes and surface areas of boxes, cylinders, and spheres. The secret here is to realize that every 3D shape is just a 2D shape with an added dimension. A cylinder is just a circle that's been stretched upwards. Its volume is the area of its circular base times its height. A rectangular prism, a box, is just a rectangle stretched upwards. Its volume is the area of its rectangular base times its height. Do you see the pattern? Volume is almost always the area of the base times the height. Let's take a cylinder with a radius of 3 and a height of 10. What is its volume? First, find the area of the base. The base is a circle, and the area of a circle is pi times the radius squared. The radius is 3, so 3 squared is 9. The area of the base is 9 pi. Now just multiply by the height. 9 pi times 10 is 90 pi. That's it. You don't need to memorize a separate formula for the volume of a cylinder if you understand the principle. Find the area of the 2D base and multiply by the height. Over these 10 parts, we've journeyed through the entire landscape of SAT math. We started with the foundational language of algebra, learning to manipulate equations and solve for x. We moved to the heart of relationships with functions and graphs, seeing how one variable can tell the story of another. We learned to interpret the world through data, statistics, and probability. And today we've given all that abstract math a physical home in the world of geometry. The real secret to the SAT was never about being a math person. It was never about memorizing 100 different formulas. It was about learning to see the patterns. It was about understanding that a complex word problem is just a simple equation in a costume. It's knowing that a terrifying diagram is just a few simple triangles hiding in plain sight. The test is designed to look intimidating. It's designed to make you panic and forget the simple truths you know. Your job isn't just to do the math. Your job is to stay calm, read carefully, and find the simple, elegant path that is always hidden within the problem. This isn't just test prep. This is mental training. You've learned how to break down a complex system into its component parts, how to identify the signal through the noise, and how to apply fundamental principles to solve a novel problem. That is a skill that will serve you far beyond test day. It will serve you in college, in your career, in your life. You have the tools. You have the strategies. You've seen the patterns. Now go and show them what you know. Don't just take the test. Go solve the puzzle.